Hey everyone! So over the next few videos we're going to introduce a handful of different identities that'll help us evaluate all sorts of different kinds of trigonometric expressions. And the four I'd like to start with in this video are the angle, sum, and difference identities. So these identities, which I'll introduce in just a moment, will help us evaluate expressions involving sums and differences in the inputs of our sine and cosine functions, right? So things of the form sine of u plus v, sine of u minus v, cosine of u plus v, and cosine of u minus v, where u and v, these are just some angles. And so maybe to give you a more explicit example, let me write down cosine of pi over 3 minus pi over 4. So let's say I wanted to evaluate this expression here. Now, pi over 3 and pi over 4, these are angles we're very familiar with evaluating cosine or sine at. But pi over 3 minus pi over 4 is an angle that we're actually not very familiar with altogether. Right, so what is pi over 3 minus pi over 4? Well, if I wanted to subtract these two fractions, I need to make a common denominator. And so that common denominator would be 12. And so I would have to multiply that first fraction by 4 over 4 to get 4 pi over 12. And that second fraction by 3 over 3 to get 3 pi over 12. And when I take this difference, we get pi over 12. So this expression here is really equivalent to cosine of pi over 12. And so pi over 12 is not an angle we're familiar with evaluating sine and cosine at, but notice that it came from the difference of two angles that we are very familiar with. So the idea behind the angle, sum, and difference identities is that we'll be able to evaluate expressions like this, where the input angle can be rewritten as the sum or difference of two angles we're very familiar with. So before I write down the actual angle, sum, and angle difference identities, the ways we evaluate these sorts of expressions, I want to show you one way that we cannot evaluate these expressions. So here, one mistake I see quite frequently when someone is trying to evaluate sine of u plus v is that they just try and distribute that sign. They'll write sine of u plus sine of v. And this might feel like a natural idea to try. It's an understandable mistake. Where oftentimes we'll see parentheses and we'll visualize multiplication, but those parentheses, they represent the input to our function. Right? This is not multiplication here, and so sine isn't something that we just multiply through to our inputs. This is not valid, and maybe I'll show you a very explicit example. Right, so sine of, let's try pi over 6, something we're very familiar with, plus pi over 6. Right, so pi over 6 plus pi over 6, that's the same as 2 pi over 6, or in other words, pi over 3. Right? This is really the same as sine of pi over 3. And so the true value of this expression, well, we know what sine of pi over 3 is, right? If I draw my unit circle, pi over 3, well, it's a rough unit circle, but pi over 3 gives us our 60-degree angle, and sine gives us that long side of that 30, 60, 90 triangle along our unit circle. And so this is the square root of 3 over 2. Now what if we tried to do the mistake I wrote above? What if we tried to write this as sine of pi over 6 plus sine of pi over 6? Well, pi over 6 corresponds to this 30-degree angle out here. And sine of pi over 6 is 1/2. And so this would give us 1/2 plus 1/2, and that's equal to 1. And this is not the same as our true value of our expression. We know square root of 3 over 2 is the true value of sine of pi over 6 plus pi over 6. So all of this work here, this was wrong. And so we cannot break apart our sine function across that sum or that difference in this this way we might expect. And maybe just to really convince you, show you another example. Let's say we had cosine of pi over 2 plus pi over 2. Right, so the true value of this expression would be cosine of pi. And pi, right, that corresponds to an angle 180 degrees. And cosine of that angle, well, that would be -1. And if we try to break this apart as cosine of pi over 2 plus cosine of pi over 2, well, at pi over 2, we're at this 90-degree angle. And cosine of pi over 2, the x-coordinate at that point is 0. So here this would give us 0 plus 0, which is definitely not equal to -1. So again, this is just another illustration of the fact that we can't evaluate cosine or sine in this way. So I've listed out the 4 different sum and difference identities here, and I don't expect you to memorize these in this class. For the exams, I'll definitely include these different identities here so you don't have to memorize them. But if you plan on continuing to do mathematics for a good while after this class, I would definitely recommend memorizing 2 of these, namely sine of u plus v and cosine of u plus v. So the other 2, they come from the 2 that I've starred. And also, identities we'll discuss in the near future will come from these identities as well. And so by remembering these 2 that I've starred, you'll be able to really remember many of the different trigonometric identities we'll cover in this class. And so it'll save you a lot of memorization down the road by memorizing these 2. So, I won't spend time justifying these identities in this video. I'll justify one in a future video, and there will be an activity that'll cover how you can get from 1 to the rest, justify all the remaining identities from 1 that we've proved. But let's go ahead and use these identities. So let's evaluate the expression we wrote down earlier. So earlier we wrote down cosine of pi over 12, and this came from cosine of, well, it was pi over 3 minus pi over 4. And so how do we evaluate cosine of pi over 3 minus pi over 4? Well, here in this identity, we have the expression involving cosine of a difference, and we have a difference here. And so here this tells us that to evaluate cosine of a difference, well, first we want to take cosine of our first angle, what we're calling u, so cosine of pi over 3, multiply that with cosine of pi over 4, right, the second angle, add that with sine of the first angle, sine of pi over 3, times sine of pi over 4. And so that's how we evaluate cosine of this angle difference here. And now what's cosine of pi over 3? Well, cosine of pi over 3, this is, maybe I'll draw the unit circle. So at an angle of pi over 3, where we have a 30, 60, 90 triangle, and cosine gives us that x-coordinate along that 30, 60, 90 triangle, this is 1/2. Now cosine of pi over 4 corresponds to the 45, 45, 90 triangle, and cosine of that triangle, of that angle, gives us the square root of 2 over 2. Then we have sine of pi over 3, which is this side length here in this triangle. That's the square root of 3 over 2. And then sine of pi over 4, well, that's this length here. That's the square root of 2 over 2. And so, we can multiply square roots with square roots and multiply their insides. This gives us the square root of 2 over 4 plus the square root of 6 over 4, which is the same as the square root of 2 plus the square root of 6 over 4. Now we cannot combine square roots through addition or subtraction, or we can't combine the insides of the square roots through addition or subtraction, so this is as simplified as it gets. This is the exact value of our expression, cosine of pi over 3 minus pi over 4. And so one thing I want to point out with all these identities, maybe just to get a little bit more familiar with these identities, is that for the cosine identities, the cosine angle sum and difference identities, these all involve, sort of this unmixed sum or difference, right? So we've got cosine of one angle, cosine of the other angle, right? This first term involves just cosine and cosine, and then sine of one angle, and then sine of the other angle. So this is the case for our cosine sum and difference identities. But when it comes to our sine sum and difference identities, here we've got a mixed sum and difference. In other words, we've got a sine times a cosine plus a cosine times a sine. And then in the other example, we've got sine times cosine, take away cosine times sine. And so here, this is just another way to get more familiar with these different identities. The sine identities involve this sort of mixed sum or difference, and the cosine angle identities involve this sort of unmixed sum and difference. So let's do another example. Let's look at, let's try and evaluate sine of 5 pi over 12. So here we're not given a sum or a difference right away. We have to sort of see what kind of sum and difference we might be able to take, or re-express this 5 pi over 12 as. And so let's just let's take 5 pi over 12 and think about which ways we can rewrite this as. And so 5 pi over 12, one way I can see this is as 3 pi over 12 plus 2 pi over 12. Right, because 2 pi plus 3 pi, that's 5 pi. And why is this useful? Well, 3 pi over 12, that reduces as pi over 4. And 2 pi over 12, that reduces as pi over 6. And so although our expression didn't include a sum or a difference as the input of our trigonometric function, we can rewrite this unfamiliar angle as a sum of angles we are familiar with, right? So as the sum of pi over 4 plus pi over 6. And now we can use our angle sum identity for sine. Right? So maybe I'll go back up. So the angle sum identity for sine tells us to evaluate sine and cosine at our two different angles, and add that with evaluating sine and cosine at the same angles, but just the reverse, right? So sine of u, the first angle, times cosine of v, the second angle, and cosine of the first angle times sine of the second angle. And then we're going to add these two together. Right, so this tells us we're going to evaluate this expression by evaluating sine of the first angle, so sine of pi over 4, times cosine of the second angle, pi over 6, plus, well then, cosine of pi over 4 times sine of pi over 6. And so let's draw a new unit circle here. So we're going to be dealing with the angles pi over 6 and pi over 4. So sine of pi over 4, that's the square root of 2 over 2. Cosine of pi over 6, that's this distance here, that's the square root of 3 over 2. And we're adding that with cosine of pi over 4, that's this distance, which is also the square root of 2 over 2. And then sine of pi over 6, well here that's 1/2. Right, so this is 1/2. And so what we get here is the square root of 6 over 4 plus the square root of 2 over 4, which is the square root of 6 plus the square root of 2 over 4. So actually we ended up getting the same value as what we saw earlier. Okay, so we've evaluated sine and cosine at a sum or a difference of two angles, but how do we deal with tangent of a difference of two angles? Let's say I wanted to simplify this tangent expression here involving a difference of input values. Well, tangent is really equivalent to sine of our input angle divided by cosine of our input angle, right? So maybe I'll write that down on the side. Tangent of theta, well, that's really the same as sine of theta over cosine of theta for any value theta. And so here, if I want to evaluate or express in a different way tangent of pi over 2 minus x, well, this is really the same as sine of pi over 2 minus x divided by cosine of pi over 2 minus x. And now we can just use our angle difference identities for sine and cosine. So for sine, we're taking this mixed difference. Right, so this will be sine of pi over 2, sine of the first angle, times cosine of the second angle. Take away cosine of this first angle, times sine of the second angle. So sine of x. So that's the angle difference identity for sine. And then for cosine, well, here it's this unmixed sum. So we get cosine of pi over 2 times cosine of x plus sine of pi over 2 times sine of x. And now sine of pi over 2, right, this here is just 1. Right, the y-coordinate on the unit circle at an angle of pi over 2, that's 1. And the x-coordinate at an angle of pi over 2, that's 0. So this this term is canceled out here, right? 0 times whatever sine of x is always going to be 0. And then cosine of pi over 2, right, we said that's 0. Sine of pi over 2, that's 1. So here this term gets canceled out as well. So now we're just left with 1 times cosine of x, which is just cosine of x, divided by 1 times sine of x, which is just sine of x. And another way that we can express cosine of x over sine of x as is cotangent of x. So this expression that we started with, tangent of pi over 2 minus x, that's the same as cotangent of x. So sometimes we may encounter expressions involving the result of an angle addition identity or an angle difference identity. And it might be beneficial for us to actually reverse this identity. So I've got an example here where that's the case. We have this equation here where the left-hand side is actually really messy. You've got sine and cosine involved, and the inputs of sine and cosine involve two different input angles, right? 5x and 3x. And this would be impossible to deal with prior to this video, but now here we can see this expression on the left and recognize it as one of the angle difference identities or angle sum identities. And now which one is it? Well, here we've got this unmixed difference, right? So we've got this cosine times this cosine and this sine times this sine, and the unmixed sums and differences come from the cosine angle sum and difference identities. And now which one does it come from? Well, this comes from the cosine sum identity. So cosine of u plus v, this is equal to cosine of u times cosine of v minus sine of u times sine of v. And so here I can recognize that 5x, this is our first angle, 3x is our second angle. And so I can rewrite this expression on the left as cosine of 5x minus 3x. Right here, this is the result of our angle addition identity. Oh no, sorry, this should be 5x plus 3x. This is the result of our angle addition identity for an input value of 5x plus 3x. Right, so that's the left-hand side, and we still have this right side of the square root of 3 over 2. And so this can be re-expressed as cosine of 8x is equal to the square root of 3 over 2. And now we can solve this using our techniques from before. Here I can replace my 8x. I can just rename it u. And so we can solve this equation. Cosine of u is equal to the square root of 3 over 2, just knowing that u is there to represent 8x. And so here, if I look at my unit circle, right, cosine of some angle giving us the square root of 3 over 2, well, that's saying we're looking for the x values on our unit circle, or sorry, the angles on our unit circle, which give us an x value of the square root of 3 over 2. So we're looking for angles that bring us here and here. Well, here, if our angles are pi over 6, or any coterminal angle to pi over 6, we'll end up with an x-coordinate of the square root of 3 over 2. And actually negative pi over 6 would also be valid. And so here, if u is equal to pi over 6 plus 2 pi n, any coterminal angle with pi over 6, that'll be a valid value for u. Also, if u is equal to negative pi over 6 plus 2 pi n, we'll also get solutions to our equation. And now we just have to remember that u was there to represent 8x. It was a placeholder for 8x. And so let me go back and replace u here with 8x. And so if we wanted solutions to our original equation, we wanted values of x that make our original equation true, then we just have to divide both sides of both of these equations by 8. And so let's do that here. Maybe I'll start with this first one. Let's rewrite that as dividing the left side by 8 is going to give me just x. Dividing the right side by 8 really divides each term by 8. So pi over 6 divided by 8, that's pi over 48, right? 6 times 8. And then 2 pi n divided by 8, well, this factor of 2 in the numerator and denominator of our 2 pi over 8 fraction would come out to be pi times n over 4. Now, this would originally be 2 pi n over 8, and the 2 would cancel on the numerator and denominator and leave me with pi n over 4. And this is actually the same case for our second equation. If we divide both sides by 8, we'll get negative pi over 48 plus pi n over 4.